Over the last 48 hours, our sun has rapidly awakened. In just 2 days, the number of solar flares has more than tripled. Giant sunspots are emerging, and intense magnetic fields are twisting together in large active regions, one of which is now pointing almost directly at Earth. Which raises the question, is this active region storing up energy for a massive X-class solar flare? An eruption powerful enough to degrade GPS, disrupt satellites, and stress electrical grids. We have fleets of spacecraft watching every ripple on the solar surface, yet we still cannot pinpoint exactly when a magnetic system will become unstable and snap. To prepare for the next major strike, we have to look past the sensational headlines and understand why our nearest star keeps its exact timing completely hidden. The origin point for these massive eruptions starts with what we call a sunspot. Although they look dark, these aren't holes in the star. They're cooler areas on the surface, where strong magnetic fields push up from deep within. These magnetic fields are highly complex. Picture twisting thousands of giant rubber bands together to see how these magnetic lines tangle into tight structures, storing up immense energy as tension builds. Eventually, that tension reaches a breaking point. The tangled fields suddenly snap and reconnect into simpler shapes, dumping all that stored energy instantly. We call this magnetic reconnection. In a matter of minutes, this single event releases energy comparable to billions of nuclear bombs. That sudden snapping of magnetic lines is what produces a solar flare, the most powerful explosion anywhere in our solar system. To measure these outbursts, scientists sort flares into 5 categories on a chart: A, B, C, M, and at the very top, X. Because the scale increases tenfold with each step, the jump to an X-class flare represents an exponential spike in raw energy. An X2 flare is twice as powerful as an X1. But is this brilliant flash of radiation what actually poses a threat to things on the ground? No. A flare is an intense burst of electromagnetic radiation traveling at the speed of light. The physical threat comes from a coronal mass ejection, or CME, an enormous, solid cloud of magnetized plasma blasted outward into space. They don't always happen together. To feel a physical impact on Earth, a CME has to follow the flare, and that cloud has to be aimed squarely at our planet. The flare gives us an immediate warning flash, but the CME is the physical projectile that actually tests our modern infrastructure. If an Earth-directed CME is launched, that heavy cloud of charged particles takes anywhere from 1 to 3 days to cross the void and hit our planet's magnetic shield. The collision triggers a geomagnetic storm. As Earth's magnetic field compresses, it can degrade GPS accuracy, interrupt high-frequency radio communications, and induce rogue electrical currents that put severe stress on power grids and electrical transformers. But this influx of energy also has a striking side effect. It pushes vibrant auroras far closer to the equator than their usual polar habitats. The exact same charged particles that challenge our vital power grids also paint the night sky with some of nature's most spectacular displays of light. So, if we have constant satellite surveillance monitoring every sunspot, why can't we predict exactly when an X-class flare will snap? Because the mechanisms that trigger these eruptions don't start where we can see them. They begin deep beneath the sun's visible surface, completely hidden from our cameras. Even our most advanced computer models cannot perfectly simulate every interaction inside these massive submerged magnetic systems. Forecasters can calculate the probabilities, but they cannot guarantee the exact timing. Despite all our technological progress, our nearest star holds on to its deepest secrets, leaving us inherently vulnerable to the chaotic rhythms of the cosmos. We don't know exactly when the next massive flare will strike, but we will be watching. If you want to stay informed on the science behind space weather, like this video, share it, and subscribe to the channel.